class, I gave you or I told you that we are going to solve this problem, and we are supposed to determine the shape factor for a triangular section. And previous to that, we have found the shape factor for a rectangular shaped section. This one we have already found out. Okay. Now these are some of the values which I directly gave. You don't need to compute that one. Okay. Now in the question we have now we have a problem where we need to find out the shape factor for the triangular section. Okay. So now first of all, let us say that we have the section like this. This is one section. This is a right angle one. Okay, and through this line we have the neutral axis. I am showing it as NE. This one is neutral axis. Okay, and this one, the height, this one is given as H. This is given as B. Okay, and here we have the same one. Sorry. Okay, now this distance is B1 and this distance is H1. Okay, and this is the section. So this I've directly told in NA, or you can write NA here. Okay, neutral axis. Okay, now we have to determine the shape factor for the triangular section. Okay, so before we determine the shape factor, all of you please take down this diagram. Okay, so the first step what we need to calculate is, the first step is step 1. This first step is section modulus. Section modulus. Okay, now what is section modulus? That is I equals to, this already we know, BH square by, it is BH cube by 36. Okay, and from this the minimum section modulus, okay, the minimum section modulus S mean will be I by Y max. Okay, now what is the value of I? The value is BH cube by 36. And what is Y max? What is this value? Who can tell? What is this value? It is 2/3 of the what? 2/3 of H. Okay, from this diagram it is 2/3 of height. Okay, so please solve this one. How much you are getting? it is BH cube by 36, then into 3 by 2 into H. Okay, so this 3 to, yeah, this gets cancelled. So and this H and this 1H, it gets cancelled. So BH square divided by 24. Okay, this is the section modulus. Okay, now the second step, step 2, it is the plastic modulus. Okay, before I go to the plastic modulus, let me show that this one is the same base. Okay, so next step is, all of you please pay attention, because this part might not have been taught to you in any earlier classes. Okay, and whenever you go to or whenever you study your design of steel structures, okay, this you will find it difficult to understand. Okay, in steel structures this part is already there. Okay, so for plastic modulus, what we need to see, so first let us say this ratios. So please pay attention to the diagram. Can I write H1 B1 by 2 equals to half of BH by 2? Can I write like this? Okay, but we already know, but we already know that H1 divided by B1, H1 by V1 equals to H by B, and B1 equals to H into B1 by H. Okay, so from this we may say that B1 equals to H, sorry, so this is, so B1 equals to B into H1 divided by H. Okay, so if we substitute, okay, let us say, so if let us say this is equation, for example, let us say this is equation I. Okay, so if we substitute the value of, okay, so let me write, substituting equation 1, we have H1 into BH1 by H equals to BH by 2. Okay, this one. So instead, in this equation, I have substituted the value of this B1. Okay, so this implies What will be the value of h1 here? So h1 equals to h divided by square root of 2. Okay. So similarly, we can say that we can have b1 equals to b by root 2. Okay. Now, for both the triangles, okay, what will be the area? It will be, what will be the area? What will be area A1 and A2? What will be the area? So can I say A1 equals to A2 equals to half into B into H by 2. Okay, and here, since this one is the neutral axis, the stress distribution okay, so here at this position and at this position, that is, this value is, let us say, y1 and this value is y2. This is sigma y and this is also sigma y value. Okay, now here I am writing one more point. What is this y1 and y2? Okay, so y1 equals to, or y1, or you may write this one y1 bar and y2 bar. Okay, let us write y1 bar and y2 bar. So y1 bar equals to distance between the center of compression area, center of compression area, and the neutral axis. Okay, so this y1 value will be, so this implies y1 equals to h1 by 3. So what is the value of h1? So h1 is h by root 2. Here we found, here we found that okay, see, here we have found h1 equals to h by root 2. So this, so y1 is, so this implies y1 equals to h by 3 root 2. Okay, now what is again y2? Are the y2 and y1 and y2 are same? No, because y1 is for the y1 is for y1 is for y1 is for, again you are not saying anything, compression area. Okay, and y2, so similarly y2 bar equals to distance between the centroid of compression and the neutral axis. Okay, now what will be the y2 value? All of you please pay attention. So I hope you have written this y2. What is y2? So I'm writing it here. So y2 or y2 bar, whatever you may call. Okay, y2 bar. This is bar. This is bar. Okay, y2 bar equals to, please pay attention here. So it is h minus h1 by 3 into b plus, sorry, not b, it is b1 plus 2b by b1 plus b. Okay, now we already know a relation, that is, what is that relation? b1 equals to b by root 2. So this relation we will put here, where we will put here in this equation. Okay, so I can write, this implies y2 bar equals to h minus h by root 2 divided by 3 into 2b plus b by root 2 whole divided by b plus p by root 2. Okay, so this becomes, this is equal to h into root 2 minus 1 whole divided by 3 into root 2. Then this one, if you simplify, it will be 2 root 2 plus 1 whole divided by root 2 plus 1. Now you may say, sir, this one, this root 2, this root 2, this gets cancelled. No, okay, it doesn't cancel like this, just like that. Okay, so this becomes 0.15, sorry, it is equal to 0.15 48H. I know this is a bit difficult to understand, but I'll upload this video today itself. You please go back through this video. You'll easily understand this one. Okay. Now, the next one. So we have determined here. We have determined H1. We have determined B1, and we have determined the section modulus, and the plastic modulus is given as the plastic modulus is given by, or I'll write it here. Okay, the plastic modulus is given by plastic wait. So plastic modulus is Z equals to BH BH square by 4 into 1 by 3 root 2 plus 0.1548. Okay, H being taken common. So this becomes 0.0976 BH square. That is your section modulus. Okay, so we know the section modulus and we know the plastic modulus. And if you go back to your notes, what I told, what is the formula? What is the relationship? Anybody remember? So I said that SF, that is shape factor. What is the value of shape factor? So shape factor equals to MP by My. What is MP? MP is the plastic moment and My is the yield moment. Okay, so now what is MP? MP is what I told. What is the formula of MP? MP equals to sigma Y into Z divided by My is sigma Y into S. So that becomes Z by S. Okay, Z is 0.0976 BH whole divided by, what is the value of S? What is the value of section modulus? How much we have calculated? It is coming as BH square by 24. BH square divided by 24. Is it correct? Okay, so let me modify it again. It is not looking nice. So if you solve this one, it will come out as 2.34. That is the SF. Okay, now tell me one thing. We have found out the different shape factors, right? If you pay attention here, you will come to know that for diamond shape it is 2.0, for rounded shape it is 1.0, 1.70, For rectangular shape it is 1.5, for triangular it is 1.27, for elliptical it is 1.12 to 1.20. Now here you see the shape factor for this triangular structure or triangular section is coming to be 2.34. Okay, so it is way above diamond. What happened? Okay, so it is way above the diamond shaped one. Okay, so 2.34 D is definitely maybe greater than the what will, so it is greater than this one. So 2.34, this is for the shape factor is greater 2.34, it is greater than the diamond shaped one as well. Okay, so this is a problem which I wanted to teach you in this class. Okay, so in the next class we will discuss something regarding a term called as plastic hinge. Okay.